In this video, I will show you how to use definite integrals to find areas. So for example, in number 36, we need to determine the area of this shaded region. So this is the area under the curve y equals 1 over x squared and between the x values of 1 and 2. This is what definite integrals were made for. The shaded area would be represented by the definite integral with a lower bound, lower limit of 1 and an upper limit of 2 of this function. So 1 over x squared is the same thing as x to the negative 2 power. So if we evaluate this definite integral, that will give us the area that we are being asked to find. Let's go ahead and integrate. We can simply use the power rule of integration. So adding 1 to the exponent gives us x to the negative 1 power. Then we divide by the new exponent, which is just going to put a negative 1 out front. But here come the limits of integration. We'll make a vertical line, put the lower limit here, the upper limit here. This means evaluate at the upper limit and then subtract the value at the lower limit. So the value at the upper limit will be negative 2 to the negative 1 power, and then we subtract the value at the lower limit, so substituting in 1 we get negative 1 to the negative 1 power. So this is an expression representing the area right now. So technically you could give this answer on the AP test and it would be perfectly acceptable, but what if it's a multiple choice question? It's not going to look like this. So let's keep going and simplify. Well, 2 to the negative 1 power is really just 1/2. So we have negative 1/2. And then minus, okay, 1 to the negative 1 power is just 1. Notice the minus a negative aspect. So really this is negative 1/2 plus 1. And that's going to simply be 1/2. So that is the area under the curve. For problem number 40, we need to find the area of the region bounded by the graphs of these three equations. Let's go ahead and draw a sketch so we can visualize the area that we are trying to find. Let's start with the cubic function. We know that a cubic function with a positive leading coefficient has this type of behavior. But we need to know where this graph touches the x and y axis so we can picture the boundary of the area. So let's talk about the x and y intercept of this cubic function. For the y-intercept, this is going to occur where the x value is 0. So imagine plugging in 0 for these x values. So we have x values of 0. Well, that's just going to be 0 plus 0. So the y value will be 0 as well. So we know that the y-intercept of the curve will be right here, which is also an x-intercept. What about other x-intercepts? If we want to find other x-intercepts, we need to set the entire function equal to 0 and solve. So if I set x to the third power plus x equal to 0, if I factor this, I'm going to have x times x squared plus 1 is equal to 0. Using the zero product property, the idea would be to set each of these factors equal to 0. So of course we immediately get x equals 0 from the first factor. But if we set x squared plus 1 equal to 0, this has no solutions, right? If we subtracted 1 from both sides, for example, we get x squared is equal to negative 1. You can't square something and get a negative number. Or going one step further, if you took the square root of both sides, that's imaginary. Bottom line is x equals 0 is the only x-intercept. So there will be no other x-intercepts. We don't need to know exactly what the graph looks like, but let's take the fact that we have no other x-intercepts and we know that the end behavior is something like this. To make just a rough sketch, it's okay if the graph doesn't look exactly like this. Okay, now we can turn our attention to the other two boundaries. So the area is bounded by the line x equals 1. X equals 2. So this is a vertical line at 2. So here we go. 1, 2. So this is a boundary. And of course, y equals 0 is just the x-axis. So I'm going to color in the shaded region. So this is the area bounded by the three equations we were given. Well, look, this area is the area under the curve between 0 and 2. So this will be perfectly represented by the definite integral from 0 to 2 of the cubic function, x to the third power plus x dx. So all we have to do is evaluate this and we'll have our area. Let's start by integrating the cubic function. With the power rule of integration, we will add 1 to this exponent, and that gives us x to the fourth power. And then we divide by the new exponent, so we have 1/4 in the front. Same with the next term. We add 1 to the exponent, and we get x squared. Then we divide by 2, and we have 1/2. But this is a definite integral, so we must evaluate from 0 to 2. So here are my limits of integration, which remind me to evaluate at the upper limit and then subtract the value at the lower limit. So let's start with that upper limit. If I evaluate at 2, I will have 1/4 times 2 to the fourth power plus 1/2 times 2 to the second power minus. Okay, now I'm going to evaluate at the lower limit. So this would be 1/4 times 0 to the fourth power minus 1/2 times 0 squared. Obviously, this second part just has a value of 0. Okay, 0 to the fourth power is 0, 0 squared is 0. All of this has a value of 0. So I'm going to disregard this for the rest of the problem. Evaluating the first part, let's see, we have 2 to the fourth power is 16. And then 1/4 of 16 is 4. 2 squared is 4. And then half of 4 is 2. And then, of course, this adds up to 6. And that will be the area bounded by these three equations. Let's do one more example. For number 44, we need to find the area of the region bounded by y equals 1 minus x to the fourth power and the line y equals 0. Well, we know what the line y equals 0 looks like. But what does the function 1 minus x to the fourth power look like? We've got a quartic function here that we're dealing with. We know that in general, a quartic function has end behavior that looks like this if you have a positive leading coefficient. But notice that this is really y equals negative x to the fourth power plus 1. So really we have a negative leading coefficient. So we are expecting an end behavior that looks, more like this. So if we want to get a sketch going, we really need to know what the x-intercept and y-intercept will be. So let's start with x-intercepts. Actually, let's start with y-intercept because that's always the easiest. For the y-intercept, it will always be 0, something. So we can just substitute 0 for x and then find out what the y value would be. If we put a 0 right here, it's just 1 minus 0, so y equals 1. So this is the y-intercept. What about the x-intercept or intercepts? For the x-intercepts, you set the entire function equal to 0 and solve. So if I set 1 minus x to the 4th power equal to 0, if I want to solve this, I'm going to factor. But this is the difference of two squares. So if we factor this, we're going to get 1 minus x squared times 1 plus x squared. Using the zero product property, we will set each of these equal to 0. So 1 minus x squared equals 0, and then 1 plus x squared equals 0. The 1 plus x squared, we immediately know this will have no solution. If you were to subtract 1 from both sides, this is what we saw in the previous problem. We get x squared is equal to negative 1. That's not possible. So our only x-intercepts will come from this factor. Adding x squared to both sides, we have 1 equals x squared. If we take the square root of both sides, we get x equals plus or minus 1. Please don't forget the plus or minus. You know what? I guess another way we could have thought about it is this is the difference of two squares again. So another way you could think about it is this is 1 minus x times 1 plus x. So either way, we will end up with x equals plus or minus 1. So we have two x-intercepts and the y-intercept. This should be enough information for us to sketch the graph. So here's 1, and here is negative 1. And here is 0, 1. So we have our y-intercept at 0, 1, and we have the x-intercepts here and here. We don't need to know exactly what the curve looks like. We just need to know the boundary. So I'm going to draw a curve that looks like this. But it doesn't matter if it doesn't quite look like this. What matters is that it intercepts the x-axis here and here at negative 1 and positive 1, and it goes up to the y-intercept of 0, 1. We are looking for the area that is between the quartic function that we just drew and the x-axis. Because of this, y equals 0, that's the x-axis. So we are looking for this yellow area. Well, guess what? This is the area under the curve from negative 1 to positive 1. This would be perfectly represented by a definite integral. So this would be the definite integral from negative 1 to positive 1 of the quartic function 1 minus x to the 4th power. So let's evaluate this. We can integrate each term separately. The integral of 1 is just going to be x. And then time for the power rule of integration. We will add 1 to this power, so we will get x to the 5th power. And then we divide by that new power, so we have a 1/5 in the front. But we need to evaluate from negative 1 to positive 1. So I will put my limits of integration here. And this will remind me to evaluate at the upper limit and then subtract the value at the lower limit. So let's see. Evaluating at the upper limit gives us 1 minus 1/5 times 1 to the 5th power. So that's the upper limit. So now here comes the lower limit of negative 1. So we have negative 1 minus 1/5 times negative 1 to the 5th power. So this expression represents the area of the yellow region. So we could leave it just like this and get full credit on the AP test as long as that's all they were asking for was the area of the shaded region. But if this was a multiple choice question, it's not going to look like this. So let's keep going and simplify this down further. So this will be 1 minus, well, 1 to the 5th power is just 1. So we have 1 minus 1/5. And then for the second part, we have -1. -1 to the 5th power is -1. So we have -1 times -1/5. So this will be plus 1/5. All right, let's go ahead and distribute this minus sign. So we have 1 minus 1/5 minus -1. So this is plus 1 and minus 1/5. So let's see, I'm looking at 1 plus 1, so we have 2. And then we have -1/5 and another -1/5, so that will be -2/5. So if I wanted like denominators, I could multiply this by 5/5. So I'm looking at 10/5 minus 2/5. So that will be 8/5. And that is the area of the shaded region.